Hey Math 206, we're wrapping up section 12.4 on similar triangles. The mid-segment of a triangle is a segment that connects the midpoint on one side of the triangle to the midpoint on the other. So it turns out that that segment is parallel to the third side of the triangle and is half as long as that third side of the triangle. So why is that? Let's go through thinking about why that would be. First of all, if you're thinking about the triangles BMN, the smaller triangle, and the larger triangle BAC, first I want to explain to you that these two triangles must be similar. Well, for sure, they share the angle B, and also, if I call this length here, if I call this X, then the longer side is twice X, because this and this are the same. If I call this side length Y, then this longer side is twice Y. So, because this length and this length are the same. So is that side angle side similarity? Triangle BMN is similar to triangle BAC. Okay, so because the triangles are similar, so then you get for free that all the angles are congruent. And take a look what we have here. These are corresponding angles. So since the corresponding angles are congruent, the lines are parallel. So corresponding angles congruent means MN is parallel to AC. All right, and then the third thing about this being twice this side length, well, because all the sides are proportional, this is X, this is twice X, here's Y, here's twice Y. If I call this side length Z, then this side length, because it's proportional, has to be twice Z. So because sides are proportional, side AC is twice whatever the side MN was. All right, so that's mid-segment. They have lots of great properties. And it turns out also, if a line bisects one side of the triangle and is parallel to a second side, then it must bisect the third side. So let me draw you a picture of that. You have a triangle and a line that bisects one side of the triangle, so chops it into two equal sized pieces, and is parallel to the third side of the triangle, then I can conclude that it bisects the third side. So why is that? Well, it's because if it's parallel to the base here, you've got these congruent angles, and you know that if the larger triangle here and the smaller triangle here, they also share this vertex angle. So by angle, the small triangle and the large triangle are similar to each other. So therefore, all the sides are proportional and all these segments are proportional as well. So then this line here must bisect the third side of the triangle. All right, so let's use some of those ideas to say something about the quadrilateral that's pictured. You have a quadrilateral ABCD, and there's no information given about this quadrilateral. I can't even say what type of quadrilateral it is. It just has four sides. And suppose you have M, N, P, and Q here that are the midpoint of each one of these sides. And you connect those midpoints with line segments. What can we say about the resulting shape? Okay, it looks to me like the opposite sides are parallel. I'd like to say that it's a parallelogram, but I need some evidence to show that. So what I'm going to do is draw in some helping lines. Here is one of the diagonals of my quadrilateral, BD. And if I think of this triangle, BCD here, BD is the base, then NP is the mid-segment for triangle BCD. So let's write that down. NP is a midsegment of triangle BCD. So by all of this stuff we discussed up here, NP has to be parallel to BD. So NP is parallel to BD. And you can say the same thing about this triangle down here. MQ is a midsegment of this triangle, ABD. So that tells me that MQ, the midsegment, has to be parallel to the base. So MQ is parallel to BD. Therefore, since MQ is parallel to BD is parallel to NP, MQ is parallel to NP. All right, similarly, we can do the same sort of reasoning. Draw in the diagonal here, AC. That gives you this triangle above and this triangle below. And MN is the midsegment for the triangle above. PQ is the midsegment for the triangle below. So we can just say similarly, MN is parallel to PQ. So therefore, this quadrilateral that we just made, MNPQ, has to be a parallelogram. And so this is all using mid-segment properties. Let's now move on to medians and centroids. So given a triangle, we know that each side has a midpoint. And if we connect the midpoints, we get the mid-segment. So let's discuss what happens if instead of connecting the midpoints together, what if you connect the midpoint to its opposite vertex? What you get then is called the median. It's a segment connecting the vertex to the midpoint of the opposite side. So every triangle has three medians, and if you notice, the three medians intersect in a common point. That common point is called the center of gravity or the centroid of the triangle. So just thinking about what this means in context, it's the point. It's like the balance point of your triangle. It's a point where if you put your finger at that point, your triangle would balance perfectly. All right, so let's show that the centroid of a circle divides each median into two segments with length in the ratio 1:2. Focus on just a few aspects of the picture here. Look at median BN and median AM. And also let's draw in the midsegment from N to M to N. I'm going to put in a few markings here, like BM is the same as MC because it's the midpoint, and AN here is the same as NC. All right, and this MN is the midsegment of this triangle ABC, so I know that MN is parallel to AB. So that's the first thing. That segment is parallel to AB. All right, and because these two line segments here are parallel, I can tell you that some of these angles are congruent, like this angle here and this angle here, because they are alternate interior angles. So angle ABN is congruent to angle MNB, because the two lines are parallel. Also, these angles are congruent for the same reason. So angle BAM is congruent to angle MBN NMA. All right, and then you have that these vertical angles are congruent as well. Either way, by angle, you have that these two orange triangles are similar. So triangle ABG is similar to triangle NNG. All of the sides need to be proportional to each other. So first, let me figure out how the side MN and the side AB relate to each other. So in this larger triangle ABC here, MN is the mid segment, and we've seen that the mid segment is exactly half as long as the base. So since MN is a mid segment of triangle ABC, I know that this length, AB, is exactly twice this length, MN. So that factor 2 is going to be like our constant of proportionality. It's going to be the proportional factor for all the sides of my triangles. Let me focus my attention now on these two orange triangles. Again, whatever this side length is, this side will be twice as long. So now let's focus our attention on the corresponding sides here. Let me call this side length Y. This is MG. Then which side of the larger orange triangle corresponds to side MG? It's in between the angle that is congruent to M here, so that would be A, and the point G. So it's this side. So if this side length is Y, then this side length is twice Y. Let's write that down. So this tells us that side length AG is exactly twice the side length MG. And this is exactly what we were looking for, right? Because AM is the median, is one of the medians, and the point of intersection G here splits the median into two pieces, one which is twice as long as the other. Okay, and we can say similarly, BG should be twice NG, this length, and all the same logic, here's the third median. CG should be twice PG.